Let's analyze the simple pendulum using the action physics or Euler Lagrange approach. First thing we have to do is choose a coordinate system. Now, the simplest thing to do might be to choose a two-dimensional Cartesian coordinate system, maybe centered on the pivot. As soon as we start to think about how to formulate the problem in that way, we run into the constraint that the pendulum mass is moving on a circle, so that x squared plus y squared is equal to the length squared, where the length is the length of the pendulum rod. And it turns out to be quite difficult to incorporate that constraint into the equations. So Cartesian coordinates doesn't seem to be a very good choice. In fact, we'll look at this more carefully when we look at the spring pendulum as another example. Really what we need to do is take into account the fact that the massless rod itself is providing a potential that keeps the bob on the circular path about the pivot. But that's really not something we want to do right now. So the way to approach this is to take advantage of the circular symmetry of the situation and use the angle theta. Now, in principle, we're also using the r coordinate, so we'd be using polar coordinates, but r is fixed at L by the rod, so we're only left with 1 degree of freedom, which immediately means that this is a simpler approach than Cartesian coordinates, because we only have one coordinate that's changing, namely theta. So the way to proceed is to write down the kinetic energy, and that's a half mv squared as usual, where v is equal to r theta dot, where r is actually L, the length of the pendulum. This comes from the arc length, S, being the radius of the circular motion times the angle. So if we look at the rate of change of that arc length, which is the velocity, well, L is fixed, but theta is not. This is a pretty important relationship, that the tangential velocity in circular motion is the radius of the motion, in this case L, times the rate of change of angle with time, theta dot. So that's the kinetic energy. There's only 1 degree of freedom. And the potential energy is due to gravity. If we take the zero of potential energy at the bottom of the swing, then the potential energy is just the height above that. And we can get the height above that by doing a little trigonometry. That projection of the length L of the pendulum onto the vertical direction is L cos theta, and the distance from the pivot to the bottom is L. So the difference between those is the height, which is pretty small in this example. That height there is L minus L cos theta, and we want to multiply that by mg to get the potential energy of the mass m in gravity. And just to check that that's right, when theta is equal to 0, cos of theta is 1, so we get L minus L, which is 0, so 0 potential energy is indeed the equilibrium point. The next thing to do is to write down the Lagrangian. And next, the Euler-Lagrange equations. The first part of that comes from that term, because that's where the only theta dot dependence is. The only thing that depends on time there is theta dot, so it gains another derivative and becomes the second derivative of angle. The other term in the Euler-Lagrange equation is the derivative of the Lagrangian with respect to the angle theta. That's just coming from that term. The derivative of cos theta is minus sine theta, so we get, so putting all those together, we can write down the Euler-Lagrange equation for the simple pendulum. And we can simplify that a little bit by cancelling out ml. And we can get even more insight by dividing through by L. So what that immediately tells us is that whatever the solution to this equation is, it only depends on the ratio of g, the acceleration due to gravity, to L, the length of the pendulum.